All right, so there is one little caveat. Sometimes curves intersect each other more than once, like these two in this picture. So this guy's f of x here, and this guy's g of x down here. All right, so what happens then? Well, you have two pieces then, because you have your formula is your top curve minus your bottom curve to find the area between curves. So you're going to have to go from A to B, and, excuse me, A to C. C is where they actually intersect. Right here at C is where they intersect again, and they intersect at A. So from A to C, f is on top. So you do f of x minus g of x dx. But then we need to add on the area from C to D, but from there, g is on top. So now you need to do g of x minus f of x. So be aware if you intersect more than once and you're asked to find area between curves, you need to do it in parts because the top curve isn't always the same on the entire interval. All right, so here's an example of that. What if I want to find the area bounded between the graphs? I should put the word between of this parabola, y equals x squared minus 3 and negative x minus 1. All right, this is a little bit awkward. Usually you only do the area between the intersection points, but I wanted to show you some things. So negative 4 and 3 is where you want to go to. Oops, here's 3. All right, so how would I do that? Well, between the curves over here is this spot. All right, between the curves here is this spot. I'm going to add the word between here, okay? You might want to also. Between the curves here is this stuff, okay? So it switches several times. All right, so we're going to set this up. I'm not sure I'm going to actually solve it for you. You can either do it on your calculator or not. But these intersect here at negative 2, it looks like. Just to double check, let's see if I do negative 2 squared right here. Negative 2 squared, that's 4, minus 3 is 1. If I do negative 2, it is 1. So it is actually intersecting. They have the same solution there, and this one also is at 1. You can double check that if you really must. I'm right, but okay, so we're on the first little bit from negative 4 to negative 2 where they intersect. I am having my top curve of the parabola, x squared minus 3, and then I have to subtract the bottom curve, which is the line, okay, dx. And then I have another area, but now it switches. So from negative 2 to 1, the top curve is actually negative x minus 1. And my bottom curve is x squared minus 3. And then I have another one where I go from 1 to 3 to finish out my integral. To finish out my interval with my integral. Okay, so that one, again, is the same as this guy. The first one, the x squared is on top, the parabola is on top, and the line is underneath. So you have to find each of those pieces. Either one is a really difficult integral to solve by hand. You should be able to do it by hand, but you can do it on your calculator. I'm not going to actually solve it out. Setting it up is enough for right now. All right, so we're going to also just set this up. So finding the intersection points, we're going to do that on our calculators. It says the sine and cosine curves intersect each other infinitely many times, as shown as this diagram. Find the area of just one of those regions. Okay, so one of these regions. Maybe it would be better to find this one because of the positives involved. All right, so where do we go? So I found the intersection points right here, and they happen at pi over 4 and 5 pi over 4. Okay, if you need to be convinced of that, think of your unit circle where sine and cosine the same, well, at a 45, 45, 90 triangle right here at pi over 4. And also they're both negative down here at 5 pi over 4. All right, that doesn't even look like a 5. Let me fix that a little bit. So I'm going to do that. So the intersection points are at pi over 4 and 5 pi over 4. I don't really care what the y values are at the moment to set up my integral. So to set up my integral, I'm going from pi over 4 then to 5 pi over 4. And we have to figure out which is on top. Well, cosine is the red, because cosine starts at 1, and sine is the blue. So at least in our area, sine is the top curve, and cosine is the bottom curve. All right, had we chosen that first area where I'd be going from pi over 4 to negative 3 pi over 4, now cosine would have been on top. That is another way to do it. You would be just using a separate interval, but it should give you the same area. I'll let you compute that on your calculator. You could do that one by hand as well. Okay, this next one is a you try it. Stop the video, do it, and see if you can get the same answer as I do. I will be just mostly writing answers and not explaining as much, so you might need to come back with questions. All right, so this first step is to graph them and find the intersection points. Okay, so my intersection points are from negative 2 to 0 and 0 to 2. The next step is to set up the integral. So in the first part, from the negative 2 to 0 interval, my area has f of x on top and the g of x on bottom. I color-coded those. And on the next part, g of x is on top from 0 to 2. The g of x is on top, and the f of x is on bottom, so you have to switch them. Okay, to calculate them, go for it. You should be able to do it by hand. I forgot a dx here. Let me add it in. Go ahead and do that by hand, but I'm going to write the answer down so you can check it when you're done. And so my answer for each part happened to be 12 by a fluke. And so total, I get 24 total area for between my curves.